You're watching a Channel 98 NBISD TV production.
Hey, welcome to Deja Vu. It's Algebra 2. As always, I'm your host, Kevin Corpy. Today I've got lesson 29 all bundled up, ready to unpack for you. We're going to be talking about ellipses today. That's day 2 of our 3-show segment on conic sections. You're not going to want to miss it. So download those worksheets from the district website. I worked so hard in creating them for you. Grab a sharp, pointy pencil and stick around for about 30 minutes or so and learn something about ellipses. All right, lesson 29. Conic sections continued. Ellipses today. Now remember, I brought my little cone, my little breakaway model of my cone last week, and we said that a circle is something that you get when you slice a cone parallel to the base. Well, how do you get an ellipse from a cone? It's a conic section after all. Well, if you tilt that little parallel plane that you sliced parallel to the base, and you tilt it a little bit at an angle, cut through the cone, but you still come out the other side, the cross section is an ellipse. It looks something like that right there. The darkened shaded region forms an ellipse, okay? And when you look at it face on, it's like a circle that's been kind of scrunched horizontally or scrunched vertically, okay? It's not perfectly round, it's oblong. In fact, many people call the ellipse by its more common name, the oval. And that's really all an ellipse is. But the ellipse is a much more precise mathematical name. And we are going to be doing some precise calculations with an ellipse. So, let's go ahead and get to the locus definition of an ellipse. Now remember, every single conic section has a locus definition. Locus meaning a set of all points such that. Okay, for the circle, it was all the points that were equidistant from a fixed point called the center. That fixed distance was called the radius. Well, an ellipse is going to be slightly different. It starts off the same way. It's the set of all points such that. Now, it's the set of all points such that the sum of the distances, that's plural, to two fixed points, not one fixed point anymore, is a constant. Okay? The sum of the distances to two fixed points is a constant. This right here is a nice demonstration of what that is. This outer edge right here is the actual ellipse. If we think of this as being a particular point on the ellipse, then the distance from here to here, we're going to call this our fixed point, which is actually called a focus. And then to the other fixed point, which is over here, that's the other focus, together making up the plural version foci, or foci, however you want to say it. That distance from the point on the ellipse, we'll call this one D1, call this one D2. If you add those two distances together, at any point along here, you get a constant. Now that constant is going to come into play into the equation. We're not going to derive the equation today like we did the circle. If you go on to take pre-calculus, you'll see the derivation, or if you ask your Algebra 2 teacher to see it, I'm sure they'd be happy to do it for you. Okay, so what we have here then is D1 plus D2 is a constant. So what are these two fixed points? They're the foci again, and they are set in from the circle. They're not actually on the circle in much the same way that the fixed point for the circle, the center, was not actually on the circle. Okay, you can think of this now as being a circle essentially with two different radii. From the center, and this would be the center of our ellipse, we have a certain distance from here to here and a distance from here to here. And they're going to be different for an ellipse. After all, if those two were the exact same length, we would be back to our traditional circle. But because they're different, we actually have an ellipse. Now, the longer of the two versions is going to be called the semi-major axis length, and then the smaller one is called the semi-minor axis. And what we do is we traditionally use letters A and B to denote those. So the semi-major axis length is going to be called A, so that's going to be here, and the semi-minor axis length is B. It's always the shorter one. Now notice where the two foci are in relation to the lengths of the axis. Okay? All the way across from here to here is called the major axis, and these points at the end of the major axis are called vertices. Okay? The endpoints of the shorter axis, which is called the minor axis, are called co-vertices. So longer axis, major axis. Endpoints, the vertices. We have the shorter distance being the minor axis. The endpoints are the co-vertices. The 2 points are the foci. Back to my original question. Notice that the foci are on the longer axis, and that's not by coincidence. In fact, if you were to create this ellipse by getting a piece of string that has a certain length, and then you would bring the endpoints in a little bit and pin them down, you can put a pen in the end of your string there and trace out from the slack of the string. Those foci, the points that you pin that string down, will always be on the longer axis or on the major axis, and that's a very important thing when working with ellipse. The foci are always on the longer or major axis. Got it? Okay, so there's the anatomy of an ellipse. Let's go ahead and give you a better breakdown of it, because this diagram here can get a little bit kind of confusing. Here's a little more colorful version of the ellipse. We've got the minor axis being the shorter one. We've got the major axis being the longer one, which is horizontal. Notice these foci are going to be on the major axis. Now we can also have ellipses that are longer vertically than horizontal, and the foci would be on the vertical axis. This just happens to be one of 2 types. Notice the center is at the origin. We're going to start off by looking at ellipses that are centered at the origin. If we call then the center at the origin and the semi-major axis is A, then the vertex would be to the right A units and up 0. So it would be at the point A0. Similarly, if we go to the left A units, it would be at negative A0 at the other vertex. If we call the semi-minor axis B, the length of it B, then to get there, in this case, I go up B units, which is the point 0B for the co-vertex, and I go down B units to 0, negative B for the other co-vertex. Those are the co-vertices. Now, the focal distance, or the focal length, is going to be the distance from the center to either of the 2 foci, and we usually use the letter C for the focal length. Therefore, the focus in this case would be right C units and up 0. So one focus is at C0 and the other one's at negative C0. So there's the anatomy in color now of an ellipse. A is the semi-major axis, B is the semi-minor axis, C is the focal length, and it's always on the same axis as the major or longer axis. Got it? Okay. What we're going to do now is look at the typical equations for an ellipse in standard form centered at the origin. I'm not going to derive them for you again. That would kind of be beyond the scope of this show. We'd run out of time, I'm afraid. So there's 2 different versions you want to think about here. An ellipse that opens side to side, longer on the side, and one that opens vertically, where the major axis is vertical. Centered at the origin. The horizontal variety is going to look like this. Okay? X squared over A squared plus y squared over b squared equals 1. Okay? Now notice if a squared and b squared were the same, I can multiply everything through by that, and I'd be back at my standard equation for a circle. But because we have 2 different radii, essentially, I can't just get a single number on the other side. The coefficients of x and y are going to be different. So another way to write that equation, unlike the circle, is to divide through by a squared and b squared, and we have a 1 over here. Now this is going to be a pretty typical standard form for the rest of the conics that we work with. You can even write equations of the line like this, where this would be without the squareds would be your x-intercept and your y-intercept. So it's not an uncommon form. But this is going to be the horizontal version where the major axis is horizontal. So that would open side to side. Now notice A is always longer than B. So A is always greater than B. That's important. When it opens horizontally, your A is beneath the x, which is your horizontal axis value. Your B, the shorter one, is underneath the y, which is your minor axis. But if it opens vertically, the longer axis is vertical. Now notice your A, which is always greater than B, is underneath the y. So your semi-major axis is beneath the y, which is a good implication from the equation that opens vertically. And your B, your semi-minor axis squared, is underneath the x squared. Okay? So that's a real easy way to remember it. A is always the semi-major, bigger axis. B is the semi-minor. If it's under the x, it opens side to side. If it's under the y, it opens vertically. Okay? Now we're not quite ready to start looking at equations yet. There's one last little piece of the puzzle that we're going to need here to work with these equations. And that is a very special relationship between the focus and the vertices and the co-vertices. Okay? It's one equation that relates all three variables. Now, the derivation of this is pretty easy. It comes from basically the Pythagorean theorem when you're looking at A, B, and C. Again, I'm not going to derive it on the show today, but it can be done and it's not that difficult. But notice that it's not quite the Pythagorean theorem. It's a squared minus b squared. And that's because a and b aren't necessarily the shorter legs of a right triangle. It is derived from that. C, A, and B have very specific meanings now in the context of what we're doing. C is the focal length, A is the semi-major axis, and B is the semi-minor axis. You have to get that straight. Now notice that on the equation of the ellipse, it's always x squared plus y squared in both cases. But for the equation that relates c squared to a and b, it's a squared minus b squared. It's the opposite sign. Okay? That's going to be important because that pattern is going to hold true for the next conic that we look at next week. So c squared is a squared minus b squared. That allows you to find the focal length if you know the semi-major and minor axis, or it allows you to find either of the two axes lengths if you know the focus and the other one. Okay? It's a formula. If you know two of the three, you can find the third. All right. Let's go ahead and practice now. We want to sketch the ellipse with the following equation. Notice it's 25x squared plus 9y squared. This is not a circle. Think of the 25 and the 9 as being vertical dilation factors on the separate axis. Because those are different dilation factors, it's like taking the circle, which would be x squared plus y squared, and stretching it by different factors on the x and y axis, which will make it oblong, which makes it an ellipse. Now this is not the standard form. The way we get it into standard form is to try and create a 1 over here. And we do that not by subtracting 224, because that won't always work. We do it by dividing. So whatever we have over here, we have our constant isolated. We divide both sides of the equation by that number. And to do that, I'm going to divide all three terms by that. Now this one works out pretty nicely. 225 divided by itself is 1. 9 2/25. What you want to do is you want to simplify that as a fraction. That is the same as 1/25. So I end up with y squared over 25. Plus 25 2/25 simplifies to 1/9. So that's going to end up with x squared over 9. This right here is my standard equation. Now, this right here is larger. 25 is larger than 9. So that must be a? No, that's a squared. A squared is 25, which means a must be 5. Okay? The smaller one is always b squared. If b squared is equal to 9, then b must be 3. And notice the center is 0, 0. That's all we need to sketch the ellipse. Notice this one's going to open vertically because the larger number is underneath the y. So I'll draw my x and y axis. You draw the center first. Everything originates from the center. It doesn't matter how you put your points, but you're going to need 4 points. Underneath the x, we have a 9, so the square root of that is 3. X is always horizontal, so from your center, you're going to do a little polka here. 1, 2, 3 to the right, 1, 2, 3 to the left. Okay, that defines your width. Underneath the y, we have 25, the square root of which is 5. So it's under the y, so that's up and down. So from the center, we'll go up 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If I put a point now on each of those, I have 4 points that I can connect. And all we have to do to finish our ellipse then is connect them with not a square, not a rectangle, but with a nice smooth curve. Okay, so it's going to look like this. And you get pretty good at drawing these things with a little bit of practice. There's our ellipse. It's a little bit taller than it is wide. What we want to do now is sketch where the foci are going to be. Are they going to be on the horizontal axis, or are they going to be on the vertical axis? Which one is longer? The vertical axis is longer. Okay, so they're going to be up and down on the vertical axis. I just need to know how far away they are from the center. So I pull out my handy dandy, c squared equals a squared minus b squared. And since a is always bigger than b, a squared is always bigger than b squared. So here we go. C squared is equal to 25. Remember that was a squared minus, remember 9 is b squared. 25 minus 9 is the nice number 16. So c is equal to really plus or minus 4. And that's just the directions that we go from the center. So we go up in this case. So up 1, 2, 3, 4. We have a focus right there. And down 1, 2, 3, 4. We have the focus there. Now depending on what your teacher expects, you may not have to sketch the focus every time. But as you're going to see at the end of the show, the foci are not only important in terms of defining the shape of the ellipse, but they also have a very unique property that you're going to want to stick around for. Let's take a real quick commercial break, watch these public service announcements. Don't go away because we're going to be right back with more ellipses. While you're gone, think about this. What did George Washington say to his men before they crossed the Delaware? The answer when we get back.
Mom!
What?
You can't find Ichabod.
What?
You don't have to be perfect to be a perfect parent. There are thousands of teens in foster care who would love to put up with you.
I smoked weed and nobody died. I didn't get into a car accident. I didn't OD on heroin the next day. Nothing happened. We sat on Pete's couch for 11 hours. Now what's going to happen on Pete's couch? Nothing. You have a better shot at dying out there in the real world. Driving hard to the rim, ice skating with a girl. Now you want to keep yourself alive, you go over to Pete, sit on his couch till you're 86. Safest thing in the world. Me? I'll take my chances out there. Call me reckless.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking to you today about not ovals, but ellipses. Very similar to ovals. Did you think about what George Washington said to his men prior to crossing the Delaware? He told them to get in the boat. We're sinking. Back to math. Another important thing that you're going to have to do beyond graphing ellipses from equations is to write equations of ellipses from specific pieces of information. For instance, write an equation in standard form of an ellipse with the center at 0, 0. Okay, that's nice. A covertex at -7, 0, and a focus at 0, square root of 13. Now, if we were given the coordinate of a vertice and a covertice, we could essentially figure out our A and B, which is all we need for the equation. You just drop them in. But if we're given the focus, we're going to be C. We're going to have C. A covertex is going to give us our value of B. Well, we're going to need to find A, and we use the little relationship C squared is A squared minus B squared. Now, what you could do to get started is actually to sketch it. It'll help you orient yourself. We have a covertex at -7, so 1, 2, 3, 4, 5, 6, 7. It's right here. That means the other one has to be over here, 1, 2, 3, 4, 5, 6, 7. It has to be on the right-hand side. Now, because we called those covertices, the x-axis is going to be the shorter side, which means it's going to be taller vertically. Otherwise, those would have been called the vertices. Now, notice this is also going to remind us of that. 0 square root of 13, if we plot that point. Square root of 13 is between 3 and 4, so it's 3 point something. 1, 2, 3 point something is a focus. Down 1, 2, 3 point something is a focus. Because those lie on a vertical axis, the ellipse is going to look like that. Well, remember I need A and B. Since the covertex distance from the center is 7 units, 7 equals B. I have that. I just need to find A. Well, I don't have A, but I can find C. C is the distance from the center to a focus, which is the square root of 13. So if B is equal to 7 and C is equal to the square root of 13, how can I find A? Well, I use the equation. C squared is A squared minus B squared. There it is. And if we carefully plug in now to the equation, I get the square root of 13 squared equals A squared, what I'm looking for, minus 7 squared. So I get 13 equals A squared, and that's minus the quantity 7 squared, which is minus 49. And if I add that to both sides, I get A squared equals 13 plus 49, which means A squared is equal to 62. Now that's not a perfect square, but remember we actually need A squared in the equation, not A. So if A squared is 62 and B is 7, so B squared is 49, those are going to be the denominators in standard form. I just need to know which one goes under the x squared and which one goes under the y squared. Remember, this thing opens vertically, so the larger number goes under the y squared. So here we go. I like to do it in 2 steps. X squared over something plus y squared over something equals 1. That's kind of your template. So that takes care of that part. Now it's just a matter of saying 62 is bigger than 49, It opens vertically, so that's going to go underneath the y squared. 49 then fits underneath the x squared. And there's your equation in standard form. Nothing to it. Now, just like we did with a circle, what if your ellipse is not centered at the origin? Well, it's going to make the equation just slightly, how can we say it nicely, augmented. It's going to have a little bit more information in it. So if our center, just like for the circles, is at the point HK, we can modify our equations. The horizontal one would be x minus h quantity squared. Just like for circles, it's still over a squared because that's the larger axis for horizontal, and then y minus k squared over b squared. If it's vertical, the center's still at hk, so it's still x minus h and y minus k. Of course, the a squared and b squared are just flipped. So that's not a big deal. You're still going to plot the center first and count your radiuses, your semi-major and your semi-minor from your center, get your points, connect the dots. Okay? Not really difficult. Let's go ahead and graph this ellipse given by x minus 5 squared over 16 plus y plus 2 squared over 36. Notice, in fact, it is ellipse because at x squared plus y squared, and we have different numbers underneath the x and y, which means it's dilated differently than a circle. So what we want to carefully do is identify the center. The center is at 5, comma, negative 2. Y plus 2 is y minus negative 2. Now we want to see if it opens vertically or horizontally. 36 is bigger than 16, so it's under the y. That's a vertical, so I know my foci are going to be on the vertical axis. That means 16 must be b squared, which means b is 4. And 36 must be my a squared, so a must be 6. Well, that's all we need to sketch the ellipse minus the foci. Let's go ahead and plot that. We first draw a coordinate plane, and we graph the center. We plot it as a point. 1, 2, 3, 4, 5, and down 2 puts us right there. Now, underneath the x, we had the 16. So the square root of that is 4. Because it's under the x, we go left and right 4 units from the center. So that's going to be 1, 2, 3, 4, put a point there, and 1, 2, 3, 4, put a point there. Underneath the y, we had 36. The square root of that is 6. So because it's under the y, we go 6 units up and down from the center. So up 6 would be 1, 2, 3, 4, 5, 6, puts me here, and down 1, 2, 3, 4, 5, 6. There's your 4 points. Now you connect them very carefully with curved lines, and again, you'll get good after you do several of these, so do a lot. Now, if you wanted to plot the foci, they're going to be on the vertical axis, and again, c squared would equal a squared minus b squared, which is 36 minus 16. So c squared would equal 20, and c would be the square root of 20, which is approximately 4 point something, which is good enough for now. If you want to plot those on there, you go up 1, 2, 3, 4 point something, and then down 4 point something, and those would be your foci, okay, which again have very nice reflective properties. Which brings us to
Deja Review.
Remember I told you that the foci have some very important properties associated with them, not just by way of the locus definition. And it's a reflective property. Now every single conic has a unique reflective property. Here's what the ellipse's reflective property is. Anything that takes off from one of the foci, whether it's a pool ball or a sound wave or a light wave, anything that is emitted from one foci will hit the outside of the ellipse, and it will bounce off or be reflected directly at the other foci, and it'll travel through that point. That's kind of cool. Doesn't matter which foci you start from or where you go out, if you hit the ellipse's circumference or the perimeter, it'll bounce off and always go through the other focus. Very important property. Now, you might have had experiences with this unique property. They have these rooms called whispering rooms or whispering galleries, which are actually three-dimensional ellipsoids, okay, or cross-sections of them. But they work on the same principle. The Chicago Museum of Science and Industry is one such place that has a whispering gallery. And basically, if you stand in this huge room, which is 47 feet 4 inches long by 13 feet 6 inches wide, you could be standing right next to somebody and whisper and not hear them. And you're standing right next to them. But yet, if they're at a particular point across the room, and you're at the particular point on the other side of the room, and you whisper the same thing, math is fun, they can hear you much more clearly than if they're standing 5 feet from you. And that's because anything that you say standing at one focus will travel in all directions, or the direction you're speaking to, bounce off the walls, and it'll be concentrated directly at the other focus where the other person is hearing it. And so your sound, that whisper, is magnified through that one little spot. Okay? And now if you're working with light waves, this could be a mirror that transmits things from one focus to the other. Another place where you might have seen this used is in hospitals. If you've ever had kidney stones, you might have had a non-invasive procedure called lithotripsy. And what lithotripsy is it works on the reflective properties of an ellipse. They sit the person down into a vat of water. Well, that vat is actually shaped like an ellipse. It's an elliptical vat. And what they do is they carefully position a patient precisely at one focus of that ellipse. Then they submerge an ultra-high frequency sound transmitter that gets here in the water, and it submits a very high frequency sound wave in all directions. Now, if that sound by itself emitted hit the person over here, it wouldn't do much good. But by magnifying it in all directions, every single one of those sounds is going to be directed precisely back through the other focus. And the concentration of that signal is enough to smash the kidney stone into much smaller stones, by which the patient can now pass it entirely on their own without any invasive procedure. Okay? So the ellipse has very unique reflective properties. You might want to look around and see if you can spot ellipses in everyday life, because I guarantee they're out there. All right, we're out of time today. Hope you enjoyed our discussion on ellipses today. That's the second of 2 conic sections that we've looked at so far. Last week was circles, this week ellipses. Next week, we're going to be talking about the parabola again, and the fourth and final conic section, which you're just going to have to tune in to figure out what it's called and why it's so important. All right, so until next time, I'm Kevin Corpy reminding you, as always, to do your homework.